For the following object, which is drawn as just this arrow, so that could be anything. The mirror, so we're assuming the shiny side of the mirror is on the left, and this is the back of the mirror where these little blue slashes are. And the eye, so how does the eye observe this object? Well, just a couple of things. For flat, also known as planar mirrors, the object distance is always equal to the image distance. So that means whatever this distance is here between the object and the mirror, the image is going to be located exactly the same distance behind the mirror. And then the other thing that's true for all mirrors is that the angle of incidence always equals the angle of reflection. We're going to make sure that that's true when we finish our diagram. So let's start by drawing a couple of rays that satisfy the first criteria, where the object distance and the image distance are the same. So we're trying to get nice predictable rays, so just pick easy ones. So let's start with the one that goes straight from the bottom of that object and hits the mirror. So something like that. Now we know that it's going to bounce off and come straight back to the object, but we want to know the line of sight where we actually see it. So remember, the object or the image itself will appear on the other side of the mirror, and that's said to be a virtual image. Same distance. So if you took a ruler and measured this as your object distance for that first straight ray, it's coming along like that. And then it'll strike the mirror, and because it's hitting it at exactly 90 degrees, it'll bounce back. But as far as the viewer is concerned, that ray of light that's bouncing back, I'll put it in pink here, will appear to come from this line here. And that image distance is exactly the same as the object distance. So in other words, the bottom of that arrow will be located here. So I'll do that in blue. There's the bottom of our arrow. Now similarly, we can do the top. So if I grab the top and do the same thing, take a straight ray from the tip of that arrow and strike the mirror, it's going to have an image exactly the same distance on the other side of the mirror. So again, DO equals DI, and my image will appear to, when it bounces off, to come along from this line here. So that will be where the top of the arrow is. So we can draw our image in now. And because the rays only appear to come from that location, let's get used to the fact that that's called a virtual image. It's upright. In other words, it's in the same orientation as the original one. And dotted simply means that the rays aren't actually there. They appear to come from there. Now let's see how the rays actually strike the eye. Well, the eye only can the brain can only interpret rays that are coming in a straight line. So what we're seeing is a ray that is originating from this image on the other side of the mirror, traveling up through the mirror and towards our eye. So let's see how that looks. So I will insert an arrow from the tip of this, and we know it's got to travel right to my eye like that. So there's the ray that we see. Maybe a little bit lower. Now I'll change the color of that so we can actually see it. Let's make it yellow or something. There we go. Similarly from the bottom. So if I get another ray from the bottom and draw it right to my eye, I will have established what the eye actually is observing. Okay, there's our two observed rays. Now, a few technicalities. The rays that are bouncing off the mirror are on the left. These are the rays, these are actual rays. The other ones are the rays that appear to us to be traveling straight. We can't interpret the bounce. So we think these rays are traveling in a straight line along these dotted pink paths, like that. But let's just summarize what we did. Straight line from the bottom of the ray equal distance on the other side. Straight line from the top of the object, I said ray, from the object, equal distance on the other side. And then top and bottom make lines right to our eye. And now we just have to see how all of this plays out in terms of an actual ray diagram. So remember, light, when it hits the mirror, the angle of incidence equals the angle of refraction. So, or reflection. So this angle right here between the normal line and this ray that we think is coming from the bottom, that's the reflected ray. I'll call that angle R. The angle of incidence should be right here, and it should be exactly the same. I'll label that angle I. So you could take a protractor and measure those angles, but what you'll end up getting, if I just insert one more line here, is a ray that looks like it's traveling from the bottom of the mirror, striking the mirror right at that point, and then traveling up to my eye. So we've got a ray that travels from the bottom of that image, strikes the mirror, angle of incidence equals angle of reflection, then it hits my eye, and to our eye it appears to travel along that straight line. Similarly for the top ray. So a ray traveling from the tip of that arrow will strike the mirror exactly at this location, bounce off, and we should see that the angle of incidence equals the angle of reflection. So let's try that ray, and that should finish it. So from the tip of the arrow to that location, and again, I'll just make it yellow so we can actually see it. And let's just trace these rays out. I've got a ray traveling towards the mirror. Anything towards the mirror is an incident ray. It hits the mirror and bounces off, and this pink is the reflected ray. And if I drew a little normal line, which is 90 degrees to the mirror right there, my angle of reflection, this little angle right in there, should be exactly the same as the angle of incidence. And I think you can see that it actually is. So that's the correct ray diagram for a planar mirror for that image.